today we're going to look at just pulling this together. We've talked about row ranks. Did we talk about Scooby-Doo in here? When I say row rank, I think of Scooby-Doo. Yeah, and Astro on the Jetsons, probably the same actor. Column rank of A is the dimension of the column space. So these were a little difficult for us, but what they're trying to do is that when you get A, you get a row rank from the reduced row echelon, you get the column rank, and those should compare to each other. Before, the row rank and the column rank and the rank in general were the same. So the same thing is true for the transformation matrix. So all that we're going to do with that is we're just going to analyze this because it's going to be an indicator of whether we can solve or not. Yes?
So just to clarify, going back to basics,
no.
The column space is like the columns of the matrix, right?
A matrix A, yeah. They're saying matrix A. And I think with A, with the row rank and the column rank, what we were trying to do is they were reduced. And so that we saw two answers, and then that gave those column ranks two answers. So it'll make sense when we look at this one. So we're going to verify that this is true. Row rank, column rank, and the rank of T are the same. So the first thing we're going to do is we're going to take this example, 1, 1, 0, 2, and so on, times B. Notice it's not square. And we're going to find all of these ranks. So the first thing you're going to do is what? To A. What are you going to do to A first? Inverse. Okay? Take out your calculators. Let's do it. Go ahead and find, not inverse, please. Let's find the reduced row echelon. Yep. You're right. Of A. Reduced row echelon form of A. Just do it. I want to double check to see that we get the same. So we checked in class, we get this row reduced echelon form of A, which is just you have this set of equations, you take the coefficients, you make A, and this is what you would multiply by X, Y, Z, and you maybe have a W, you'd have 4 in there, W, X, Y, Z. And then what you're going to do is you're going to reduce this so that we can say, all right, this is the column vector, the row space, the basis row space of A. 1, 0, 1 half, negative 1. It's the row that has a leading 1 to it. This is all 0, so that doesn't work. And how many of these are there? 2. So we would say that there is a row rank of 2. Now the column rank of that would be, this is the first row, second row, so we would take the first column, second column to get those. So that's the column space. Good review. Basis of the column space here. So then it says, but the range of the column space of A, so the rank must be equal to 2 as well. So the range, rank T is going to be equal to 2. So that's how that part worked. And they were saying the system of linear equations, AX equals B, the rank is equal to the transformed rank. And that's something we're going to see next. With this one, now what we're going to do is see if you're able to solve this, that it's consistent with finding a solution. And remember that this is underspecified, and you might say, well, we can get any answer we want, right? Not necessarily. You might not be able to solve for it. So we have to prove that it's consistent, and the way we do that is by analyzing the ranks. If the ranks are equal, then we can solve it. It's consistent. If the ranks are not equal, then we can't. So with this one, they're saying that if you have X, Y, Z, 1, 2, 1, 1, 2, 1, negative 1, negative 1, 2, 4, 7, B is going to be this column. And then what you'll do is you're going to put this into, well, they looked at the row rank, and you can do the row rank here and see that these will all be zeros. So it looks like A is going to be equal to 2. Rank of A is equal to 2, because when you don't put B in the picture, you're going to get a rank of 2. When you do put B into the picture, we do an augmented matrix. We just tack that on there, then do the reduced row echelon form, and what do you see happens? There's a 1 here. That means we've got a third rank. Or I would just say, is 1 ever equal to 0? No. So that disproves that we can solve it too. Either way, it's inconsistent if you count the ranks using that theorem, or if you just say, oh, when you do this, we have a rank of 2, here we have a rank of 3, but if you do this, 0 is equal to 1, so there would be no solutions for that. Is that unsettling when you don't get any solutions? Don't be. Be cold and mathematical. So what? We don't have an answer to life's problems. The math doesn't work. No, don't feel that way, but the answer, if you don't get an answer, it's fine. Well, there will be a particular solution. So what we mean by a particular solution is you're going to find a solution on inspection. And this annoys all of you. You want them to give you at least a point, right? But they're not always going to do that. You're going to have to come up with your own. And it's infinite number of points you could pick. But some of them are going to be pretty basic, as we'll see. Every solution can be written as a series, as a linear combination, and the vectors, well, these constants are a solution. So what that means is that you're going to do everything you did before, but you're going to make a standard matrix from the solution. And then they proved it. I thought that was fine, but this is going to be way more helpful. Use the theorem on the known solution that once you get a particular solution, plug in to a standard and find out. That's how we're going to do this. So by inspection, just look at this top one. Would you? What would be the easiest way to get 1? Easiest. Everything's 0 except x1, and that's what they did. 1, 0, 0, 0, 0. So would you highlight all of those zeros? And then I'm going to highlight this 1 here. Now what we're going to do is we're going to create a standard matrix. And to create it, we're going to use this particular solution, plug these values in, and make this. So corresponding homogeneous, they've got a 1 here. Let's see. Yeah. So they made the standard matrix from this, 1, negative 1, negative 2, 3, 1. And then they did the reduced row echelon. By the way, what's the row rank of this? 3. What will the column rank be? 3 of the standard matrix, yeah. And so what they did is once they got this, they went, and what they did is they assigned these to x1, x2, x3, x4, x5, and not this part. And then what they did is they said, okay, we're going to let x3 be equal to s, x5 equal to t. I think I've seen this example before. And then what they'll do is they'll assign, okay, x1 will be negative x5, negative t, and then it'll be plus s. So that's going to be, x1 will be negative t plus s. And then this one will just be negative s. And this one here is going to be, what's this one going to be? 0. So x4 is just 0. And we've got all the rest of these. So then, if you remember, see how nicely this works as a review? x1 is s minus t, x2 is negative s, x3 is s, x4 is 0, and then x5 is t. So can you see how we get 1, negative 1, 3, 0, 1, negative 1, 1, 0, 0, negative 1, 0, 0, 0, 0, 1, and then where in the world did that come from? That was the point. That was the solution. So this right here is my solution, particular solution that we had. This is the basis without it. And then that's going to get me my, what are they looking for here? That's my basis of solutions, where S and T are elements of the real. Kurt and Jacob asked me if they why this was added, and I appreciate it. If any of you wondering why I just added this on? Yes, you should. So let's go back. Let x0 be a particular solution. x0 is a particular solution for this linear combination. Now the linear combination of this made our matrix, our standard matrix, right? So if we want to know x, we can add x0 to that linear combination or to that standard matrix, and then we'll have the solution. They proved that here. If x0 is a solution, ax0 is b, okay, because it's a solution. This would work, right? That's what solution means. And so b is ax. Why is that? Because ax equals b. Okay, so then if we move it to one side, pull out the a, you'll get x minus x0, and x minus x0 is in the null space. We can put this, wait a minute. What's x minus x0 equal to if we're going to get 0 here? 0. What was this sum equal to for a linear combination? 0. So if x minus x0 is 0 and this is equal to 0, then x minus x0 is that, and we can add that x0 over. I just surprised myself. All right. Let's do it. Let's do it. You try 1a and see how that goes. We're going to do 1a, b, and C, and then we'll check for consistencies 2A, B, and C. Except, I think what I'm going to do is we're going to do 1A together, 2A together, and 3A together.